So we're going to be solving the complex numbers test written a couple of weeks ago. In question number 1, we're given two complex numbers, z and w, and we have an a. We need to do z minus w. When we sub in there 1 plus 3i, which is the value of z, minus and the value of w is 8 minus 3i, we just get 1 plus 3i minus 8 plus 3i, which means minus 7 plus 6i, which is the answer to the first question. Then part B states imaginary part of z times w. What is the imaginary part of a complex number? When z is equal to a plus ib, we say that the real part of z is a and the imaginary part of z is b. Careful, not bi, just b, okay? Good, so we need to find first the product and then take only the imaginary part of the product. Product would be z times w, so z is 1 plus 3i, w is 8 minus 3i. When we do this step by step, we just get 8 times 1, 8, 1 times minus 3i minus 3i, then 3i times 8 is 24i, and then 3i times minus 3i is minus 9i squared. And I squared, definition of I is root of -1, or I squared is always equal to 1. So this is just positive 9. This is positive 9. So 9 plus 8, 17 plus 21i, because I need to do 24 minus 3. Therefore, the answer to the problem, which is not the product, but the imaginary part of the product, is just equal to 21. For question C, we have w divided by the conjugate of z. So how do we divide complex numbers? We don't have a definition of that operation as a normal division that we could use in real numbers. What we do is we need to get rid of the imaginary part. This thing we just talked about here, we need to get rid of the imaginary part so that we don't have an I in the denominator of the fraction, and then we can just use the real part of the number to simplify with the number on top. So what we need to do for that is to get rid of the imaginary part of the denominator. How do we do this? So for solving for getting rid of the imaginary part complex number, what we do is we multiply a plus ib times a minus ib, which is what we call conjugate of the number. If z was equal to a plus ib, this is z times the conjugate of z. Why do we do this? Because when we expand this, we'll just get a squared plus abi minus abi. These part will cancel out, minus I squared b squared. I squared is minus 1, which means that this is just a squared plus b squared. We can use this from now onwards. This part will cancel with that part, and therefore the product of a complex number times its conjugate does not have an imaginary part. This is why, for getting rid of the denominator here, what we need to do is multiply and divide by the conjugate of z. You can just see that this question, the top is the operation we just did in the question before, which means that the numerator will have 17 plus 21i right away. But we still need to see what happens with the denominator. The denominator is z times z conjugate, z 1 plus 3i, conjugate of z 1 minus 3i, and then in the top we can just use the answer from the question before to write this here. 1 plus 3i times 1 minus 3i. I explained how to do it here, but I'm just going to do a numerical example, not just leave it with letters. So we've got there 1 plus 3i times 1 minus 3i. When we multiply this, when we expand this, we just get 1 minus 3i, and then plus 3i finally, minus 9i squared. This cancels with that. And I squared is equal to -1, which means that this is just equal to 1 plus 9, 10. So what we get here is 17 over 10 plus 21 over 10i. And now we've got the right form in the number. So let's go to question number 2 now. Question number 2 is 2 parts. Part A is write the complex number I to the power 23 plus 2i squared minus 1 in the form a plus bi. So first thing we've got there that we need to get rid of is I to the power 23. How do we get rid of that? So we know that I is equal to square root of -1. We know that I squared is equal to I times I, which is equal to -1. I to the power 3 is I times I squared. Can just use what we just calculated here. I squared is -1. Therefore, I to the power 3 is just minus I. And I to the power 4 is I squared times I squared. And I squared definition is -1, which means that this is just equal to 1. So the sequence we get here is first we've got an I, then -1, then minus I, and then 1. Why do I stop here? Because I to the power 5 is just going to be I times I to the power 4, which is just I times 1, which is just I. Whoop, we're back there. I to the power 6 is I squared times I to the power 4 again. I to the power 4 is 1, which means that this is just I squared times 1, which is just -1. I'll go back there. So from there on, we just get these same answers repeated. So the question is how many cycles of 4 times we get there. We're not going to talk about modulus function, but 23 divided by 4, because we have 4 different possible results, is equal to 5 remainder 3, right? So if remainder is 3, that means that we are going to complete 5 cycles of the 4 possibilities, and we'll just get 3 left. 3 left means 1, 2, and 3. So I to the power of 23 is equal to -I. That's the first part. -I plus 2i squared minus 1 is equal to -I plus 2 times I squared is -1. So it's -2 minus 1. So what we actually get here is -3 minus I. And this is the required form. Part B, we need to calculate the real and the imaginary part of these complex number. We need to transform these complex numbers to the form a plus ib, so we can find the real and the imaginary part. For this, we need to expand first the denominator of the part on the left, which is 2 minus I squared. 2 minus I squared is 2 minus I times 2 minus I. When we expand this, we just get 4 minus 2i minus 2i plus I squared. I squared is equal to -1, which means that this is 3 minus 4i. This complex number, the first part of the complex number is now 1 plus I divided by 3 minus 4i, and we just did before. For solving this, for getting rid of the denominator, we need to multiply times the conjugate of the number, up and down. So 3 plus 4i down, 3 plus 4i up. And we just get in the bottom, it's just gonna be 25. And in the top, we're gonna get 1 times 3, 3, 1 times 4i plus 3i. And then I times 4i is gonna be 4i squared, which is minus 4. So this number is just going to be minus 1 plus 7i divided by 25. Now we've got this part, which is this part, and the other part. So we could do it now, or we can just put all the number with common denominator so that we can just transform to the form a plus ib. When we do this, we just get minus 1 plus 7i divided by 25. Well, not 25. Well, yeah, 25. 25 minus 5 plus 3i divided by 2. Common denominator here has to be 50. That's minus 2 plus 14i. And then we're just going to get the minus 125. And then we're going to have to multiply 3 times 25 as well, which means minus 75i. And when we expand this, we get minus 127 divided by 50 as real part, minus 61 divided by 50i, which implies that the real part of z is equal to minus 127 divided by 50, and the imaginary part of z is equal to negative 61 divided by 50. Question 3. Here we need to solve that equation where z is a complex number and z dash is the conjugate of z. So if z is a complex number, z has the shape a plus ib, and conjugate has the shape a minus ib, is equal to 3i plus a plus ib plus 1. Just expand all this thing. We have 3ai. 3i times ib is just going to be minus 3b, because I squared will be equal to negative 1. Minus a plus ib is equal to 3i plus a plus ib plus 1. And now we need to split this into different equations. First equation will be the one with the imaginary part of the equation. All these numbers, it's going to be the real part of the expression before. It's going to be, sorry, the real part, not the imaginary part. Start with the imaginary part. You can start with any of them, but I just started with the imaginary part. I'm not going to write real part. 3a plus b is equal to 3 plus b. We can simplify this. Well, we can simplify this a lot, like a is equal to 1 right away, because b's will cancel out here. B's will cancel out, and 3a equals to 3, which means a is equal to 1. Then the real part of this expression, we just take the real part, which is minus 3b here, minus a plus a, and 1. Good for us that we know the value of a. Get minus 3b minus a is equal to a plus 1. Using a is equal to 1, we just get minus 3b minus 1 is equal to 2, which means that minus 3b is equal to 3, which means that b is equal to negative 1. So after solving all this equation, we just get that z is equal to 1 minus I. So question 4 now. Question 4 states solve the equation z squared is equal to minus 16 plus 12i, which means that we need to find a complex number z such that the square of the complex number is equal to minus 16 plus 12i. How do we do this? Well, first we need to treat z as a plus ib. Then z squared is a plus ib times a plus ib, which means a squared plus 2abi. Then we need to do plus ib squared. Plus ib squared is going to be plus I squared plus b squared, so minus b squared. There. Good. Once we've got this structure, we need to identify that structure with the complex number that we are given. So we get that a squared minus b squared plus 2abi has to be equal to minus 16 plus 12i. Note that this is just coming from expanding the number z is equal a plus ib squared. Good. Now that we have this, as we did before, we need to split in this equation in one side the real part, in a different side the imaginary part. So the real part of that equation is a squared minus b squared equals negative 16. And the imaginary part of that expression is 2ab equals to 12. So you can see we just get a system of simultaneous equations with two equations. Now we need to solve the system of simultaneous equations. From equation number 2, we get that a times b is equal to 6. Therefore, a is equal to 6 divided by b. Now we can insert that in equation number 1. And we just get 6 over b squared minus b squared is equal to negative 16. That we can expand to 36 over b squared minus b squared is equal to negative 16. That is not really useful because we cannot solve unless we just multiply everything times b squared, getting 36 minus b to the power 4 is equal to negative 16b squared. When we get this thing, we get an equation that has a polynomial that has degree 4 and degree 2. This is a big quadratic equation, and we can do the change of variable t is equal to b squared. Therefore, t squared is equal to b to the power 4. And with this change of variable, we transform the equation to, the original equation is b to the 4 minus 16b squared minus 36 equals 0. We transform these to t squared minus 16t minus 36 equal to 0, which is the same as t minus 18 times t plus 2 equals 0, which means that the two possible solutions for t here are t equal to 18 and t equal to negative 2. So, considering the change of variable that we use for finding t, that we can see here, t is equal to b squared, the solution t equals negative 2 will not give us a real number. And here we're assuming that a and b are real numbers because of the definition of z, right? The imaginary part and the real part of a complex number are real numbers, even if z itself, it's a complex number. Therefore, we can just forget about the part that says t is equal to negative 2. But t is equal to 18, we cannot forget about that part. That's the one we have to use. So if we undo the change of variable, we will get that b is equal to plus minus the square root of 18. Of course, 18 is 2 times 3 times 3. The square root of 18 is the square root of 2 times 3 times 3, which means 3 root 2. So b is basically plus minus 3 root 2. Good, we've got b. Now we need to find a, and a is here. We've defined with use the equation number 2 for getting that value of a, and now we just get this value of b. So we can find the values of a as follows. If we get that b is equal to 3 root 2, then a is 6 over 3 root 2. We don't really write root 2 in the denominator, so we need to rationalize that expression by multiplying and dividing by root 2. Well, and 6 divided by 3 is just going to be 2, right? So we just get 2 divided by root 2, and 2 divided by root 2, we can multiply up and down by root 2. And root 2 would cancel with the 2, so this is just equal to root 2. These root 2 times root 2 is 2, that cancels with that 2. So first solution that we found, z can be root 2 plus 3 root 2 times I. Good. Do we actually get a second solution? I wanted to highlight this 1 second. Do we actually have a second solution? Well, let's see if we have a second solution. If b is equal to negative 3 root 2, then a is just going to be negative 6 over 3 root 2, which means that doing the same thing we did before, we're just going to have minus root 2. Therefore, the other possible solution would be minus root 2 minus 3 root 2 times I, which is the second possible solution to the equation we got. And with this, we solve the equation given above. Finally, question number 5. Find all real and complex solutions of the equation 8x squared plus 4x plus 5. This is a second degree equation, and the most common way for solving the second degree equation is using the ABC formula. So A is equal to 8, B is equal to 4, and C is equal to 5. Formula states that x is going to be equal to the minus b, so minus 4, plus minus the square root of b squared, 16 minus 4 times a times c, divided by 2a. Good. Minus 4 plus minus the root of 16 minus, that's 20 times 816, divided by 16, which is equal to negative 4 plus minus the root of 144 divided by 16, which is equal negative 144. Sorry, I'm just going to write this. It's 16 minus 106 is negative 144. And what do we do with the root of negative 144? So we need to get rid of the minus we've got here, right? Because we cannot find we cannot easily find in real numbers the root of a negative number. So what we do is we rewrite this as 4 as well, root of negative 1 times root of 144 divided by 16. Now that we've got it this way, we know that this is just going to be I, right? So this is the same as negative 4 plus minus 12i divided by 16. Of course, we get two solutions here, the plus and the minus, and we need to simplify the numerator and the denominator. So the two solutions that we will get here are going to be x1 equal to negative 1/4 plus 3/4 of I, and finally negative 1/4 minus 3/4 of I. And these are the two solutions that the equation given above has, 1 and 2. Finally, before we end the video, just wanted to mention that I've done this step by step, and a lot of the steps that I've done here can be simplified, and some questions can be approached in a faster way, but I thought that this was the most comprehensive way to explain all the questions, even going into depth with some part of the theory that you need to.